Okay, for these next problems we need to create a model to represent each of the equations shown below. So the first equation is 7 equals x minus 2. So I can represent 7 on the left side of my equation, the left side of my scale, with 7 chips. And unless I do something to indicate that they're negative with a key or with a minus sign inside, we can assume that they're positive. Then on the right side we have 2x. We were using cups to represent x, empty cups, or cups where there was a certain number of chips hidden inside. So you can show cups, or you can show x inside a square or any kind of symbol to represent x. And then plus 2, so 2 chips on this side. And there's the model. Number 6, we have 5 plus 3x equals 8. The 5 can be represented by 5 chips. And then 3x, we just need 3 x's. I'll just put them inside boxes this time. So I have 5 plus 3x, and on the other side of the scale we have 8, so 8 chips. Number 7, 2x minus 4 equals 6. So I have 2 x's. Now how do we show that we're subtracting 4? Well, we know that 2x minus 4 is the same as 2x plus negative 4. Keep, flip, change. So I can represent 4 negatives by making it clear that these chips are negative 1. Or I could make a key with 2 different symbols to represent positive 1 and negative 1. We have positive 6 on the other side, so just 6 chips. Number 8. Circle all of the following equations that have y equals 21 as an answer. So we need to solve all of these. Right now we're subtracting 11 from y, so I'm going to add 11 to undo that operation to isolate the variable, to add 11 on both sides. Minus 11 plus 11 is 0, so we have y equals 21. So it looks like that's our first correct answer, but we always check it. Y minus 11 equals 10. Put 21 where y is. 21 minus 11 equals 10. 21 minus 11 does equal 10, so y equals 21, and there's one of the answers, or one of the equations that has y equals 21 as an answer. On B we have 11y equals 121, so we need to undo this multiplication with the inverse operation, which is division. Divide both sides by 11. 11 over 11 is 1, so we have 1y equals 121 divided by 11 is 11. So y equals 11, so that one's not going to work, but let's check it. 11y equals 121. 11 times 11 equals 121. That's true. So y really does equal 11, but that's not one of the solutions to the question that was posed in the beginning. Y over 3 equals 7 for part C. We're dividing by 3, so I have to multiply both sides by 3. Inverse operation. 3 over 3 is 1, so we get y equals 7 times 3 is 21. So it looks like that's one of the solutions we're looking for. Y over 3 equals 7. If y is really 21, then 21 over 3 should equal 7, and it does. 21 divided by 3 is 7. So C is one of the answers. On D, 2y equals 42. So I'm going to undo this multiplication by 2 by dividing by 2, inverse operation. 2 over 2 is 1, so y equals 42 divided by 2 is 21. When we check it, y is 21. 2 times 21 equals 42. It does. So there's another solution. E is a little trickier. 105 divided by y equals 5. So to make this a little simpler, we're going to multiply both sides by y. Because then these y's will cancel. Y divided by y is 1, no matter what y equals. Even if y was negative 50. Negative 50 divided by negative 50 is positive 1. So we're left with 105 on the left side and 5 times y, or just 5y on the right side. Then we can undo that multiplication by 5 by dividing by 5. 5 over 5 is 1, so y equals 105 divided by 5 is 21. So there's one of the solutions, and I'm going to leave it to you to plug that back in because we're running out of time to check it, and then subtract 11 from both sides here. In this case, y equals negative 21, which is not what we're looking for. Again, I'm going to leave that to you to plug that back in because we're running out of time on the video, but you'll see that if you plug negative 21 back into that equation to check it, it does work out. Okay, we'll pick up with problem 9 on the next video.